Okay, so this is question number 12 of the nuclear physics homework booklet. So in question number 12, we are given some information about potassium-42. So we're told potassium-42 decays and it's got a half-life of 12 hours. And when this potassium isotope decays, it emits beta minus particles and also gamma rays. So it's given out both two of the three types of nuclear radiation. We're also told that if it's a freshly prepared source, it's got an activity of 3.0 times 10 to the 7 becquerel. So there are 3.0 times 10 to the 7 decays per second altogether. In part A, we're given some information. So we're told that if you need to determine a dose of radiation that's received by a person who's working with this source, the number of gamma ray photons that is incident on each square centimetre of the body has to be known. In other words, we have to know how many gamma ray photons hit every single square centimetre of this person's body. We're given some extra information, so we're told that 1 in every 5 of the decaying nuclei produces a gamma ray photon. So we've got lots of nuclei, but only 20% of them, only 1 in 5 will actually produce a gamma ray photon. 4 out of 5 of them basically will produce beta decay. Now, this scientist is working at 1.5 meters from a fresh source, so we know it's a fresh source, so it'll have this activity up here, and there's no shielding, which basically means none of it's absorbed, so we can assume that whatever's given out basically is absorbed by the person. We're asked to show that at this particular time, roughly 21 gamma ray photons per second are incident or hitting each square centimetre of the scientist's body. Okay, so there's lots of information in the starting part of this question, but we're going to use most of this. So we know for a fact that the activity of this particular source of radiation is 3.0 times 10 to the 7 becquerel. We know that because it tells us up here, and we're told that it's a freshly produced source of radiation. So that's the activity. So that's the number of decays per second, but we also know that only 1 in 5 of those decays produces photons. So the number of gamma ray photons is 3 times 10 to the 7 divided by 5. So the number of gamma ray photons that's given out per second is basically 6.0 times 10 to the 6. So this is how many gamma ray photons are given out in every single direction per second. So because they're given out in every single direction, they basically form a sphere around the source. And we're going to think about a sphere that's got a radius of 1.5 meters. The reason for that is because the person is 1.5 meters away. So we want to know, as these gamma rays spread out, once they get to a sphere of 1.5 square meters, how many of those gamma ray photons are within a square centimetre? So what we're going to do is this. We're going to say, right, okay, so the area of this sphere is 4 pi r squared, because that's your formula for the area of a surface area of a sphere, and I'm going to do everything in centimetres. The reason for that is because I need to know how many photons are incident on each square centimetre. So I could do it with square metres and then convert to square centimetres, but it's actually easier if I just work with centimetres all the time. So the area is simply 4 times pi times 150 squared. So if I do that on my calculator, it gives me this number here. So the number of photons that are incident or hitting every square centimetre of that sphere is the total number of photons altogether that's spread out divided by the area of the sphere in square centimetres, and that'll tell me how many photons there are per square centimetre. If I do that, it gives me 21.2, etc. So basically 21. So we've shown, because we've given this number here, we've basically shown that 21 gamma ray photons are incident on every square centimetre of this person's body. We're then told that the scientist goes away and he comes back 6 hours later. He works at exactly the same distance. So in other words, nothing has changed whatsoever apart from the fact that it's now 6 hours later. We're asked to calculate the new number of gamma ray photons incident per second on each square centimetre of the scientist's body. Well, basically what's happened is that the activity, this number, will have gone down because these as they decay, the number goes down and activity is proportional to the number. So actually, there are now going to be less photons given out per second than there were to start off with. So we know from the question up here that the half-life of this thing is 12 hours. So the half-life is 12 hours. So that means what I can do is I can work out the decay constant. Now I'm going to be a little bit sneaky if you like. I'm going to work out what the decay constant is in per hours. It simply saves me from working this thing out in seconds, really. So this formula still works. The decay constant is the natural log of 2 over 12, which gives me 0.0575 per hour. I can then take this and substitute this into here. And the reason I can use this as hours is because I'm going to use the time in hours as well. So provided the decay constant's in per hours and the time's in hours, which it is because it's 6 hours up here, I can use per hours. I don't have to change into seconds. So the activity is equal to the starting activity multiplied by the exponential of minus lambda t, where lambda is this number I've worked out over here, t is 6 hours. I put my numbers in. The starting activity was 21 because that was how many photons were hitting per square centimetre. E to the minus lambda, this number, multiplied by 6. And if I do that, I get 14.87, so roughly 15. So basically, this scientist, instead of absorbing 21 photons for every square centimetre of his body, is now absorbing 15. So we're then asked, at what distance from the source could the scientist now work and go back to receiving the original dose of 21 photons per second per square centimetre? So this is an inverse square law question again, because basically what he can do is if he now moves closer, then basically more photons are going to be hitting him. Because again they're not spreading out quite so much. So this is very similar to a question we've done before. If we think about the inverse square law, and we can do because it's gamma ray photons, we can only do this with gamma ray photons, then the intensity at one point is equal to a constant divided by the distance of the first point. The intensity or the count rate at the second point is equal to the same constant as here, divided by the new distance squared. So like I did in the previous question, if I rearrange this, so I get k equals I1 x1 squared, k is also equal to I2 times x2 squared. The two k's are equal to each other, so I can put these two things together, so that's equal to that, and I can just put my numbers in. The starting intensity when after these 6 hours was 15, because that's what we worked out in the previous question. The distance was 1.5 metres, so we'll keep that as metres here. That's equal to 21 because that's what we want the count rate to be at our new distance, multiplied by the new distance squared. So if I rearrange this, I get that x2 is equal to the square root of 15 times 1.5 squared, this side, divided by 21. And if I do that on my calculator, I get 1.26 metres, in other words, around about 1.3 metres to two significant figures. So this person can move 20 centimetres closer than he was before. Finally, we're asked to explain why we don't need to consider beta particle emission when we're determining the dose of radiation the scientist receives. Well, basically, the question's really asking, why does the beta radiation not actually reach the person? Because if the beta particles did reach the person, we would have to consider beta particles in the dose of radiation he gets. So we're asked to explain. So we need to say why, and that's really important for the second mark here. So the first mark is that beta particles range in air is much less than 1.5 metres. That's why we don't have to actually consider beta particle emission. Basically, the beta particles won't get to him. Why? Because beta particles lose energy rapidly because they ionise the air as they travel. So we've basically given a reason for why it is that beta particles don't have a very big range. So that was question number 12 of the Nuclear Physics Homework Booklet.